So for the Unit 2 example, we're going to cover some of the things we learned, Unit 2, so some of the low-level programming. The situation is we're trying to read a remote control receiver, and the receiver emits a very special kind of PWM signal. It emits a pulse 250 times per second, and the pulse is between 1000 and 2000 microseconds. And of course, if it's 1000, it's like 0% control stick, and then if it's 2000, it's 100% control sticks. So we're trying to read the time that the pulse is high. So that's between the 1000 and 2000. We're trying to measure the length of the pulse. So to do this, I'm using the following code. There's the variables we'll need. And in the setup, you notice we're using the pin change interrupt control register, and we're enabling pin change interrupt enable 2. And this basically enables an entire bank of pins, or like an interrupt for an entire bank of pins, 8 pins. And then the pin change mask register, it enables only like a specific pin. So here we enable the interrupt for the bank, and here for the specific pin that we want to use. And that's, in this case, Arduino Uno pin 2, a digital pin. So basically and it's a pin change, right? So if it goes from 0 to 5 volts, so from 0 to 1, then it triggers an interrupt, and also when it goes from 1 to 0, it triggers the same interrupt. And then the interrupt service routine is handled by this. And what it does is it takes the current time as the interrupt is happening, and then it needs to differentiate between whether the pin goes high or whether the pin goes low. So here is the case for when it goes high. And this is just to make sure that, or just to differentiate between like when it goes high and when it goes low, this variable. So we're checking that, and then here in timer 1 we store the current time. So that's when it goes high. Then we start the timer basically. And then this interrupt service routine should trigger another time when it goes low. And then since we set this thing to 1, or since we set this thing to 0, this will be true, and this won't, and this won't. So this piece of code will run. Here we set the last and 1 to 1, so this code will run next time. And in the channel 1, so the output, the channel 1 of the our remote control, we do the current time, which is this time when the interrupt fires, minus the timer 1. And note that here, this timer 1 variable is still from the time when the pin change went up. So this is the time when the pin went down minus the time when the pin went up to get the timer signal. So that's the entire, up time. And then here we print that. So if we go to the serial monitor, and I turn the flight controller on, it looks something like this. And then when I go to 0, it's 1000 microseconds. And then when I go to 2000, it's 100%. That's 2000 microseconds. And this is the middle, 1500, 50%. And if I plot this, of course, it'll look a little nicer. You can see directly as my stick changes output. And the nice thing about this piece of code is it can be expanded to like basically all of the Arduino pins. Of course, then you get weird timing issues where if you have like a interrupt at the same time on a single bank, then yeah, you might miss a couple interrupts, but that doesn't really happen with this setup. Yeah, in this setup I only have like one channel, but you could also have 4 channels, and it's scalable to basically any amount of channels. So here's the code for 4 channels. It's same idea. Um, yeah, so the thing is about the low-level code. This code is it's both much faster. It runs in only few clock cycles of the CPU, and you can actually have way more interrupts because with the Arduino function, there's actually only 2 interrupts. You can attach interrupt pin 1 and 2, I believe, and with this code you can expand it almost indefinitely. It's much faster, and that's much better because this piece of code came out of drone code. So I programmed my own drone. So it was really of utmost importance that this was as fast as I could make it.